If the scientists, engineers, and entrepreneurs are to be believed, space will soon be buzzing with a new breed of spaceships, piloted by a new generation of astronauts. And many of these space scientists believe that our nearest planetary neighbor, the Moon, will play a key role in these new initiatives. To them, our Moon offers everything that the next phase in the development of space is going to need. And the good news is that, in astronomical terms, it's right in our own backyard.
In a way, we're really lucky because we have this object orbiting the Earth that's so close that we can get to. You can go to the Moon anytime you want. There's a launch window open 24/7. It only takes 3 days to get there, and it has the materials that you need to create space flight capability, and it has them in the form you need them in. It will allow us to build a system to let us go anywhere. And I think that's really the ultimate goal of spacefaring. You want the ability to go wherever you want to go with whatever capability you need to do whatever job you can imagine for as long as you want to. That's the real object of spaceflight.
It's been over 4 decades since the last human boot print was planted in the lunar dust. The date was December 1972, and the boot belonged to astronaut Gene Cernan, as he prepared to join his colleague, geologist Jack Schmitt, on board the lunar module of Apollo 17 and head for home. He had these carefully scripted words to say as he mounted the access ladder.
And as I take man's last step from the surface, back home for some time to come, but we believe not too long into the future, I'd like to just let what I believe history will record, that America's challenge of today has forged man's destiny of tomorrow. And as we leave the Moon and Taurus Littrow, we leave as we came, and God willing, as we shall return, with peace and in hope for all mankind. Godspeed the crew of Apollo 17.
Everyone in NASA and the space community knew that this would be the last Apollo mission, and that new ventures such as Skylab, the shuttle, and the space station were on the horizon. But, like Gene Cernan, most people also thought that a manned return to the Moon would not be long in coming. Few would have believed then that mankind's return would be over half a century away, in the 2020s. From its first flight in 1981, the Space Shuttle transformed manned spaceflight and enabled many new missions to be conducted in low Earth orbit, about 400 kilometers or 250 miles above the Earth's surface. Low Earth orbit, also known as LEO, is where the shuttle hosted 22 Spacelab missions, launched the Hubble telescope, and played an essential role in constructing the International Space Station. In 2011, the last shuttle, Atlantis, delivered a key module to the ISS and returned to Earth just before dawn on July 21st. It was the end of an era of supreme achievements by what had been originally conceived as a reusable, cost-effective space truck.
Shuttle originally was named STS, and it was called Space Transportation System. And the idea was that the shuttle, the actual shuttle that we know and love, was the first piece of a space transportation system. It was never intended to be the ultimate end piece. It's the first piece because it can transport people and cargo from the Earth's surface to LEO. And then from there on, you would have another vehicle that would transport them to these other localities. If we had kept with the original idea of having an incremental system that gradually expands our reach with time, that would have been the next logical step. to build a reusable vehicle that could go back and forth between the station and higher points in Earth orbit.
The problem has been a combination of cost and physics. And until now, the two have been inseparable. The physics problem is simple to state, and it's called gravity. The cost problem is equally simple to state: to defeat, or at least manage, that gravity. All objects that have mass distort the space around them and are attracted to each other as a result. And the larger the object, the greater the distortion, and the greater the attraction. It's a fundamental law of nature. And for a rocket scientist, overcoming and managing gravity poses some of the most difficult design challenges of them all. It directly affects the ease with which it is possible to move around in space, because it determines the energy that needs to be spent to travel from one place to another, or to escape the gravitational field of a planet or a moon. That gravitational field is often referred to as a gravity well.
The more mass a planet or an object has, the harder it is to escape from its pull. So the bigger planets have very deep gravity wells. As you go down the scale in size, the escape and orbital velocities become correspondingly smaller. Finally, you come down to an object that's small like the Moon, which has 1/6 the gravity and 1% of the mass of the Earth, and its escape velocity is much smaller than the Earth's.
Which is a crucially important fact when you're trying to build a moon-based space transportation system. The Earth's gravity well is the deepest in the inner solar system, a fact which leads to some startling statistics. Over 85% of the weight of every rocket launched from the Earth's surface is the weight of the fuel required to lift itself out of our gravity well, at an eye-popping $20,000 per kilogram. For the shuttle, this meant that at launch, the combined weight of the solid fuel boosters, the external fuel tank, and the orbiter was typically 2,000 metric tons, of which only 100 metric tons was the orbiter and its payload. This simple imbalance between fuel and payload is the reason why lofting a single kilogram of mass into orbit has traditionally been so expensive.
There's two kinds of mass that you launch. There's smart mass and there's dumb mass. Smart mass are things that have high information density, like a computer. But dumb mass is a ton of water or a ton of liquid hydrogen. The rocket doesn't care. It has to lift it up against the gravity field of the Earth. What we're trying to do is to move to a template where we're getting most of the dumb mass from sources other than the Earth.
And at the top of the dumb mass shopping list for space engineers is propellant, rocket fuel. And this is where the Moon enters the picture. If it were possible to generate liquid oxygen and liquid hydrogen, the two most powerful rocket fuels known to science, on the Moon, then here would be a source of propellant that would be conveniently sitting at the bottom of a very weak, very shallow gravity well at the heart of the Earth-Moon transportation system. Homegrown, locally available, and cheap, all powered by the Moon's water. Intriguingly, this would also enable future space engineers to take advantage of a theory first proposed in late 18th century France by astronomer and mathematician Joseph-Louis Lagrange, who suggested that there could be a few rather unique gravitational locations in the space between suns, their planets, and their moons.
Whenever you have two gravitational bodies, there are places around those where the gravity kind of cancels out the effect of each other.
These points are effectively the neutral buoyancy points of, they call them weak stability boundaries, but they're places in the Earth-Moon system that are easy to get to other places from, and that's why they're of strategic importance.
So depending on these locations, you can potentially set up a space station or a depot or whatever the case may be, and it will stay in space at that location with very minimal amounts of propellant to keep it there.
When you factor in propellant manufacturing on the Moon and the strategic use of the Lagrange points, the space transportation system starts to look much more feasible and affordable. And that, the space scientists suggest, is going to require a family of transport vehicles, each specifically tailored to their individual missions.
Do you want something that goes from the Earth's surface to the Moon's surface and back again? The answer is no. You're going to break that up into chunks. Okay, I want something that goes from the Earth's surface to maybe some orbit around Earth, whether it's low Earth orbit or geosynchronous or whatever the case may be. Now I'm going to want to have something that goes from Earth's orbit towards the Moon. Do I want to go all the way to the Moon, like we did in Apollo and break, or do I want to go to a midpoint, such as a Lagrange point, and then have that transportation system just go from Earth orbit to the Lagrange point and back, and then have another transportation go from the Lagrange point down to low lunar orbit or to the lunar surface. So you're kind of breaking up your system. So at that Lagrange point, if I take this approach where it is now the hub of my two transportation systems or railroads, well, I'm going to probably want to put a fuel depot there. My gas station. I'm not taking everything with me to come home. I'm only taking half of what I need, which makes my launch vehicle and transportation system smaller.
Part of this new multi-part transportation system is likely to see the introduction of a wholly new propulsion technology. It's a form of ion drive, known as solar electric propulsion.
You take an element or a molecule and you accelerate it using magnetic fields and electrical fields. Here, you can get extremely high velocities of these particles, but you don't really throw a lot of these particles at the same time. So you have two ways of going to the Moon now. With chemical propulsion, it's a fast trip, maybe not as efficient, so you probably would use that for your crew. For cargo, you'll probably want to take this slow approach, high efficiency, where the amount of propellant that you use is not that great, but it may take months to a year to transfer something from Earth orbit to the Moon. You have this balancing act, and maybe you might combine the two. Maybe you use chemical propulsion to get you out mostly out of the gravity well of Earth, and then you use electric propulsion to move around the vicinity of the Moon. To go to the Moon's surface, here again, you'll need chemical propulsion because of the high thrust you need coming down and getting off the planetary surface. So you'll probably have a combination of these types of transportation systems.